up to 1,500 farmers a year, which is quite a small number of livestock officers. So this led us to think about how could we use machine learning and develop an application that will assist farmers to reduce the diagnostics time from 4 days up to 3 minutes, and have this solution in the hands of farmers and livestock officers at farm level. After we brainstormed about the potential of using machine learning to reduce the diagnostics time from 4 days up to 3 minutes and have the solution onto the hands of farmers, we came to think about what that kind of data set will be suitable for this, to address this challenge. We have low levels of literacy and multiple languages among our communities. And images was a suitable media and a suitable data set to achieve this goal. We then went on to convolutional neural networks. And we understand that convolutional neural networks are specialized kind of neural networks that process, we understand that the neural networks, the CNNs are specialized kind of neural networks that process visual imagery. And they are very successful in practical applications, such as winning many competitions, such as the ImageNet Challenge, as well as they're applied on optical character recognition systems, and of course, diseases diagnostics. And the main goal of convolutional neural networks is to process the input image from the input and obtain the label at the end. And they are arranged in layers, where the first layer is the convolution, which is a filter, or at times also known as kernel, that processes, we'll see in a few minutes, the convolutional process, but it's also followed by an activation function, a non-linear filter, the rectified linear unit layer that introduces non-linearity to the system, followed by a pooling layer that reduces the spatial dimensions from the output of the convolutional process. The convolutional modules are repeated several times until you reach the fully connected layer, which is also known as the dense layer, where the decision takes place by computing the output scores to provide the right class at the output. I acknowledge Martin Goner on this slide on the very good course that he curated on TensorFlow and deep learning without a PhD. You have an image, in this case it's a colored image, so it has 3 channels, 3 dimensions, and the convolution, the kernel, scans the image in a patch of the image, which is a neuron. It scans the image in a given order in order to obtain, to extract the features and in turn obtain another representation of the image. We have key parameters that control the size of the output image, that is padding, which is a key parameter on convolution that involves adding pixels around the input image before convolution to control the size of the output. And the other key parameter on the convolution layer is the stride, which controls on how many pixels the filter moves over the image. If the stride is 1, it means the filter moves 1 pixel at a time over the image. And the filter here has a size of 4 by 4, and the input image colored has 3 channels, and our output channel is 2, indicating that we have 2 filters on the output layer that extract features from the image. And then the subsampling process, this is the pooling process, this is the pooling which reduces the spatial dimensions from the convolution. Therefore, at every convolutional layer, you have a different size based on the stride and padding after the convolution process. And here we have another example further explaining the convolution process, where we have the classical data set of the MNIST handwritten digits, where the image is a 28 by 28 pixel grayscale, so the input channel is 1. On the first convolutional layer, we have a filter that has a size of 5 by 5 grayscale, so the input channel is 1, and the output has 4 channels, which means the stride is 1, moving 1 pixel at a time over the image. Therefore, the output is still a size of 28 by 28, but 4 channels, meaning that those the filters extract low-level features of the image on the edges and the corners. On the second convolutional layer, where we have an output channel, 8 output channels, the depth increases of the output channels, meaning the filter extracts more complex features from the image. And with the stride of 2, the image resolution is reduced by half, so we have 14 by 14 with the 8 channels, so the output depth is 8. More complex features are being extracted. On the third convolutional layer, we have a filter with the size 4 by 4, and the input channels are 8, which are where the output from the previous layer, they become the input on the third convolutional layer. And then our output channels are 12, meaning you're extracting even more complex features from the image. And with the stride of 2, the spatial resolution is again reduced by 2 to get 7 by 7. When you reach the dense layer, the fully connected layer that has 200 neurons, the features from the previous convolutional layer are flattened to obtain a 1-dimensional vector, 7 by 7 by 12, and means all features are now extracted and giving a very complex representation of the input image. And at the dense layer, you reach the softmax, which is another activation function that classifies the input image onto 10 classes. So normally we have the 2 activation functions, the rectified linear unit activation function and the softmax. And here, the ReLU, which is normally called the gate of the CNNs, suppresses the negative responses and allows the positive ones. It means the features that have been detected are the ones that pass through the ReLU. And On the softmax activation layer, at the end where the classification takes place, it converts the output scores from the fully connected layer to class probabilities, which is computed by the exponential of the output scores divided by its norm. So you get the class probabilities, and the one which has the highest is the predicted class. I also acknowledge the work of Chris Olah when he was at Google Brain on visualization of the hidden layers. We understand that the power of convolutional neural networks is on the hidden layers, and the activation functions provide the different representations of the input image. And the work of Chris Olah was able to indicate how the visualizations of these different representations of the input image. And at aggregate level, we see that the lower level features of the corners and edges are able to be detected by convolutional neural networks at a level that even the human eye might miss. And as you go through the different convolutional layers, these features are aggregated to clear visualizations or clear parts of the image. And here is an example of a deep learning architecture, which is commonly known to many researchers, the Inception, which consists of several convolutional operations in parallel, that run in parallel, and they are very deep. So after we have appreciated the theory of convolutional neural network, how do we apply them in addressing the challenge that we have of detecting the diseases? How do we train a model that can correctly classify a set of these images of chicken images and provide the correct label for a given disease? This is the workflow that we used. The work involved 3 phases. From building the data set, it was not there. We had to build the data set, followed and then annotate it using using a given set of protocols before you actually now start the modeling process. So on the first step of building the data set, it's a labor-intensive task, which really involves physically going to the farms to collect these images. Just to share with you the experience that we went through when building this data set, we applied for the ethical clearance, but it was only released after 6 months. We had to wait for 6 months to get the ethical clearance to visit these farms to collect the data. And then once we got the research permits to visit the farms in 2 regions in Tanzania, I didn't go alone. I had to go with the livestock officers and veterinary officers to visit these farms. When you reach there, it's not a matter of only showing that paper that you have research clearance for collecting the data set and you are given permission to access the farms. It really was a process. You had to build a relationship with farmers, build trust. So at every farm that we visited, you had to take time to explain what the research was about and what we will do at the farm. And the question that kept coming from the different farmers was that, what are we going to get in return? We're giving you access to our farms. You are able to gather the data, but what are we going to get in return and when? So setting up these expectations for a machine learning researcher, that was shocking. You never expected to get that feedback from farmers. So we had to really explain the goal of the project in using layman language, that we want to develop digital tools that will assist you to detect diseases, and we hope to deliver them to you to use for free in due time. That was quite a challenge, and the fact that especially when we visited the farms that had sick chickens, farmers were depressed. So with the assistance of the livestock officers and the vets that we visited the farms with, they provided advisory service on what these farmers could do for those chickens that are sick, isolating them, and even a prescription of the suitable medicine that they were to provide them. For the case of salmonella disease, the disease is quite deadly. Once you confirm that the chickens have salmonella, you have to dispose the whole flock and the eggs, because the disease is zoonotic. It affects also humans. So even all the eggs have to be disposed. So on 2 cases of the outbreaks that we had, when we arrived at those farms, the chickens had already been disposed, and fumigation had taken place. So using that ethical clearance that we had, we inoculated the chickens with the disease and monitored the progress of the disease. And after we completed the data collection, we had to dispose the chickens and the eggs properly in order to prevent spread of the disease onto the nearby farms. It took us 1 year to build this data set. We did the data collection at different intervals. We annotated the data set using our experts, and we labeled them for the 4 classes of health: Newcastle disease, salmonella, and coccidiosis. And further, we also curated the data set for object detection task. We set aside what we call a high-level and high-quality data set, and where we collected the images and the samples, and we did polymerase chain reaction, which is a molecular biology technique for rapid diagnostics. And the labeling involved amplification of the DNA fragments for the positive cases, and cases which were negative, the DNA fragments were not amplified. And we were able to establish a high-leveled data set of 1,255 images. This data, it really indicates that these tests are very expensive. Therefore, we were only able to establish a data set of over 1,255. So after building this data set that has a total of 8,067 images, it is shared on the Open Research Repository, and until now it has been downloaded 9,000 times, which to us is really an impact of the work that we did. So then, after curating the data set, having it on the Open Research Repository, we then moved on to the modeling process, using the different architectures of the convolutional neural networks. That's our hero there, our livestock field officer that we have worked with over the years. And we went through the different computer vision tasks of image classification. Given an image, can you categorize it correctly? That's image classification. And object detection looks on to localization and recognizing a given image in a given region. So we worked on to the training data set consisted of the high quality laboratory labeled images and the farm labeled images. For the testing data set, it only consisted of the farm label data set because this will reflect the reality when using the application on the at the farm. And we used several deep convolutional neural network architectures to train the models. So we had 3 sets of experiments. The first one was the baseline convolutional neural network, which we trained from scratch and with the data set, and we obtained a good accuracy of about 83%. The other, and then we used transfer learning, with 4 different architectures to run the 3 sets of experiment. The first set of experiment was the pre-training when the base model layers are all frozen, and we obtain a good accuracy for the VGG16, Inception V3, Mobile VNet 2, and Exception. On the second set of experiment, that is fine-tuning with the base model layers unfrozen, and we pre-trained with a lower learning rate, and the accuracy improved. And on the third set of experiments, we froze the batch normalization layer on the base model in order not to update the mean and variance of these batch normalization layers, and the accuracy improved slightly, and the corresponding F1 scores for each class is indicated there. And then we see the MobileNet V2 and Exception models performing the best. The corresponding accuracy and loss curves for the 2 models that performed very well are indicated there. If we observe the loss curve of the MobileNet V2, it became stable from the 20 epochs, while the one of Exception became a bit unstable after 20 epochs, indicating some degree of overfitting. So from these experiments, we were able to recommend that MobileNet V2 is most suitable for deployment on end devices because it had a lower number of parameters, about 2.6 million parameters, compared to Exception, which had 26 million parameters. We further fine-tuned the data set on a small variant of the YOLO V8, and the results for losses on both training and validation indicated a decreasing trend, meaning it's a good model performance and there's no overfitting. And the corresponding precision and recall were increasing, indicating as well good performance in detecting the true positives. We also further worked on this set of neural networks which are bigger, the vision transformers. We used the Google vision transformer. We used the tiny and small variants, and they misclassified some classes. The tiny model misclassified 57 images, while the small one misclassified 55. So the performance is quite similar, and it is expected on vision transformer because they outperform the CNNs when the data set size is very huge. So yeah, so we were able to achieve the task of providing the correct label for each image, where we have a healthy, the second one had coccidiosis, and the third chicken had salmonella. I was supposed to put the images of the chicken droppings here, but I didn't want to disrupt you, so I put the images of the chickens. So comes the toughest part. How do we go back to the farmers? We have contributed to the machine learning community, the data set that has been downloaded 9,000 times. We have shared with the community, machine learning community, the set of experiments using the data set. Now comes the toughest part of going back to the farmers, the end. And this is where the key comes on end to end. We have to go back to the farmers with the solution, provide them with the solution in their hands. Our first attempt is a mobile application where we deployed the YOLO V8 detection model on the Android application, and also provided a chatbot, a farm advisory chatbot in English and Kiswahili. We developed this chatbot using a RAG application, one RAG application in English and another one in Swahili. Each one had about 400 sentences, and we curated these with the help of the vet. They have very strict rules that you don't give any prescription to a farmer, just advisory on the diagnostic signs of the disease and preventive proper farm management measures in order to prevent the disease. So we curated this, and we used the Llama 3 70 billion parameters as the LLM for prompting the response integrated with the RAG. One thing to note is that we used APIs to implement the machine learning model for detection and also the chatbot. So the API were integrated onto the interface of the Android mobile application. So we were happy as a research team that we've reached the end. We have the mobile app that farmers could use, and we shared the app with the different farmers that we are working with. And after a while, we got feedback. Okay, this was the feedback that farmers, we cannot have our internet on throughout. It's very expensive to have the internet on throughout for inference, and also even getting responses on the chatbot. So we had to think fast. How do we keep our solution available to these farmers that have limited internet connectivity? So this led us on to developing this application using Google's MediaPipe MediaPipe model maker framework, which allows to deploy machine learning applications for end devices. So we fine-tuned the data set on the efficient net light model, which is, and we were able to have a classification model. We were able to have, this was a video, I think it is playing, but you were able to have inference on device, so farmers would no longer need to use their internet to detect the diseases, and it is fully in Swahili language. The other thing we noted, farmers are very busy people, multitasking around the farm, so we only had one interface that you are able to take the photo or upload a photo that you had, and the detection results are indicated there in real time. We launched this one a month ago, and until now, we have 300 downloads of this app. Unlike the previous one that we had launched initially, until now, this one has 130 downloads. So really, the impact on the ground and the feedback you get from users we really have to adopt fast. So we have 2 versions of the mobile app, and we see great traction on this one that we do inference on device. It is our vision to have a multimodal application that allows for, that includes clinical signs and also detection using the chicken droppings, and provide the farm advisory. Our main issue is to really have an application that works on low resource settings, which is really my call of action to my fellow researchers here, practitioners in machine learning, that whatever applications you develop for communities, for users, please don't forget to take into account the low resource settings. This way, we will make sure we are empowering our community, we're empowering everybody in the community to benefit from AI. I understand majority of the applications we deploy using APIs, but please work on developing for low resource settings where majority of our community users lie. They're the ones who contribute to the data sets and the ones who are really doing the work in the sector that you are working on. I didn't walk alone on this work over the years. I really want to acknowledge the funders over the years. The work was first funded by the Organization of Women in Science for Developing Countries. And I also like to acknowledge with much appreciation the Deep Learning Indaba Innovation Grant, which enabled us to scale the data set from 2,000 images to the 8,000 images that was funded by Deep Learning Indaba. And the current African Women in Tech and AI incubation program that currently engaged in to really make sure we are able to take this solution responsibly to the different farmers in Tanzania. And also we have collaborating partners who helped us in ideation of this idea until the milestone we have made until now of making it feasible. We had the Delta Analytics Teaching Fellowship Program, Data Science Africa, the mechanism design for social good development group. So it's really urunana. Thank you so much.
Yeah, so we'll take like 10 minutes for questions. So any questions?
Just a quick one because I have to run. Yeah, thanks for your work. Been an admirer of the work for a long time. I use the work that you guys have done for a long time. Like going back almost 8 years about when people are thinking about AI at the edge, right? The whole part that you're thinking really of the user and what the user actually, their situation is. So this is great. I was going to ask in terms of what, if we're thinking about this in a continental way, what are the steps that you think have to be done to either allow people to think about how they can get data in their contexts, right? You're in Tanzania and you're working in that area, but then how do we think about robustness if outside YOLO, are there other ways that you were thinking about how to make it more robust, even if it then becomes miniaturized and it just runs on the phone and not using the internet at all?
Yeah, thank you so much for that question, Vukosi. Again, it's really the community to drive this, and we have opened up the source code, and we have documented this work so far in English and Swahili, and we really aim to use the community we have, the Deep Learning Indaba and Data Science Africa, to spread the word for researchers who are really working towards advancing this on the edge. So it takes a village to get this done, but would like to have this up in the different languages, in the different contexts. We collected the data set in 2 regions in Tanzania, but it is a reflection of the same diseases across the region. And we were really happy to collaborate, and we understand now we have a very rich data set in different languages. We would definitely, I will definitely make sure we open source the code up to the using even the mobile application development code. We'll outsource it so people can customize in the different languages and the context they are in. Yeah.
Hello, my name is Lydia from South Africa, and I just want to congratulate you. This is amazing. This is exactly what what our community wants. This is an example of AI by Africa, for the people at the, people who would never be able to, I don't know what to say. This is amazing. Congratulations.
Thank you.
Yeah.
Thank you. And you made me recall our livestock officer when I first showed him the app, the last one, which is in Swahili after adapting the change. He said, "This is a miracle."
Yes.
So that was the first impression of the livestock officer. But I told him, please, we're addressing a real life problem. Don't put miracles on that. Yeah. So yeah. Thank you so much for the feedback.
Yeah. My question, I think, oh yes, I wanted to say one more thing. I wanted to say, I hope that you are the first of many, many, many people from this community who is building for Africa by Africa, and considering the people on the ground, like you said, low resources, don't have internet. That is typical issues that we have. So I really hope that keeps on going, and I really hope that you mentor some more people with cool, crazy ideas to serve the community. My question is, when can we have this in South Africa and in all the other countries?
Yeah, thanks so much. As I said earlier, we are going to outsource the code, and we have a documentation on GitHub that I will definitely share on the DLI channel. We have it in English and Swahili, and I will definitely even share the source code for people of the mobile app so that you can customize it onto the South African context. Yes. Okay.
Ika here from Zimbabwe. Similar to Vukosi and Lydia, I also just want to say well done. Mine is actually not a question, just a comment to say well done. This is really great. I have a friend who comes to mind from Zimbabwe who's into poultry agriculture, and she's trying to use tech and innovation. So similar to Lydia, I would then want to see how this can come to Zimbabwe. So just well done, really encouraging on how you are using AI for Africa in Africa. Thanks.
Yeah, thank you so much. Well, I've really taken it in. We'll make sure we reach out to as many nations in Africa as possible. And I really thank this platform for making it possible. Yeah.
Thank you very much for the presentation. I really appreciate the effort you used for data collection. But you say that when you'll be doing data collection, farmers were asking you what will be the outcome for them. I want just to know, just for fun, what was your feedback for them? What did you tell them so that they become flexible to allow you to go in their farmers? Okay. That was the first one. The second one is a bit hard for me to understand. The size of the data set you used. At what time did you say that we have enough data to train our model? At which number of images did you collect it and you said that is enough to clarify that we have a good data set to provide feedback to farmers? Thank you.
Okay. Yeah, thank you so much. When we visited the farms, we didn't want to give false hopes. So things like providing incentives such as money to give us access to the farm. No, we were very clear that the fund, it is project funds that we've received to address the challenge on chicken diseases. So the main incentive we used was to provide the advisory service for free to the farmer, because we would visit a farm that had sick chickens. So the vet or the livestock officer that would accompany us provided advisory service to the farmer. And we said, we want you to be able to diagnose this on your own before you get any challenges. So that was what it was really a conversation, as I said, to build the trust and develop this relationship with the farmers. And so that is how we discussed with them. And even the ones where the chickens were healthy, we were able to even give them advice on biosecurity measures, on how they can further improve the biosecurity. And also, we were very careful to observe the biosecurity measures when we went to the farms. We would change the gears, we would use proper gears, change our shoes when you go to the farm. It's not the same as the shoes you would use when leaving the farm. So we observed all the biosecurity measures when we visited the farms to make sure these farms remain safe. And regarding the second question, literature indicates that if you have at least 500 images per class, that is good enough for training. So that was quite a minimum measure for the data set that we had. Initially, we had 2,000 images, 4 classes, so we had that distribution of about 500, at least 500 images. And when our data set increased to 8,000, so we had a very good distribution for every class for training.
Thank you. And then I would then have one last question. I'm sorry, I know there's a lot of interest, but we have to keep the time in mind. So unfortunately, we cannot take more questions, but I'm sure Dina will stay around and then we can ask more questions. So one last question is from our virtual Indara participant. And I know you've already talked about the challenges that you faced, but they also wanted to hear more about the challenge that you have faced across this throughout the period of this study and how you overcame those challenges. I know you've already addressed some of them, but in case there are some that you feel like you've missed, then a comment on that.
Yeah, I discussed during the presentation, I covered mainly the challenges we faced during the work, but we kept on going because we understood that we're doing a work that will definitely benefit the community. So what lies ahead now is having a buy-in of this app, not only by the farmers, but we have this veterinary society, the vets, the livestock officers. So we also have to have long dialogues with them, but we have very good evidence at farm level of what the outcomes have been. So, and when meeting these different audiences, the farmers and even the veterinary community, it's difficult to use the machine learning terms we use in terms of accuracy, what the F1 scores. So as a team, as a machine learning researcher, I now have to adapt onto the normal layman language to explain how the app functions, the limitations when meeting these different communities ahead. So that's what I really see as the challenge ahead, but we're bracing ourselves well for it. Yeah. Thank you so much.